Give me just 1 minute. Okay, there you go. So today we are going to probably finish our lecture on collection, our module on collection. So I was just a quick, easy module. I mean, it's meant to be a quick, easy module. We are going to look at list right now, just as an example. Okay, I already mentioned that last time. We're not going to look at sets and maps in the lecture, but I really want you to read about them in the textbook and in the tutorial. Once we are done covering lists, you should have 90% of all the concepts that you need, to be able to read on sets and maps and be okay. All right. And if you have any questions, the TA and I are available during office hour, online session. Don't hesitate. Okay. Same thing with the forum. So what is a list? That should be easy for you guys. So it's an ordered collection sequence. So that's the main difference between list and set. Okay. Set is not ordered. Map is not ordered by default. There are subclasses of set and map that allow you actually to keep track of the ordering, okay? But by default, the class set and map are not actually offering this notion of ordering. We can contain duplicate elements, so that distinguishes it also from set, okay? The characteristic of a set is that you can have an element only one time. And for maps, I mean, you can have only the same key one time. Okay, so you store key values. If you have twice the same key, then you have a problem. Okay, you override. Do not confuse trying to insert twice the same key in a map with actually having a key collision. Okay, that's totally different. Trying to insert twice the same key means that you have actually the same key value for two pairs. Okay, a collision in a hash table is something different. That just means that the hash that's computed from the key to store inside the hash table ends up being the same for two different keys. Okay, so just a little bit of clarification there. So everything we said about collection is still true. That's the point of a superclass, right? So our list interface is going to offer all the features of collection, and it's going to offer obviously some new features that make it worthwhile to have a list collection. So let's get rid of the obvious stuff. The following work just as you would think, okay? With the little remark that remove is going to always remove the first occurrence of an element. You can have multiple occurrences in a list, okay? And add and add all are going to always happen at the end of the list. Modulo does little peculiarities, okay? This is doing exactly what you would think it's doing. So for example, here we have a little fragment of code. Assuming we have two reference variables, list1 and list2, each of them referring to an object of a class that implements the interface list. So we call add all on list1 with parameter list2. We are trying to append everything that is in list2 at the end of list1. Okay. The only thing with this example is that it's destructive. Destructive meaning that it modifies list1. So we can do that also without having to modify list1. We just need to actually use our constructor to make actually a copy of list1. All right. So there we go. List3 is going to be built as a copy of list1. So we use the conversion here by constructor, and then we add at the end of list3, and we are okay. Keep in mind, one of the things we are going to discuss, one of the things that's going to come back and back again to haunt us with those slides is always, is it right through or is it not right through? Okay. Keep in mind that when you have a list of elements, you have references on those elements. Okay. So in doubt, think about an array. You have an array of, employee. This is an array of references to employee object. All right. So let's say that I make a copy of the array. So if I make a copy of the references in the array and I store them into another array, you all agree that if I swap two elements in the second array, the order of the elements has not been affected in the first array. Okay? So different things. However, if I start modifying the value of the employee object that I reference to by those two arrays, then we go back to our first lecture ever, right, when we talked about references in Java. That's the one thing that can be remotely tricky in that scenario. So what's happening? You can modify the employee. So even if I tell you, I copy a list, and those lists are independent, which means that if I reorder one of the lists, the other one is not affected. If I remove element from one of the lists, the other one is not affected. If I add element to one of the lists, the other one is untouched. Okay, that is true. But if I start modifying the elements themselves, I have references to the same underlying objects. Okay, so just making sure that you don't fall for this. Okay. So additional features that we have in addition to those add and add all and stuff like that, remove, essentially positional access and search. These are the first one we are going to cover in the upcoming slide. Iteration, we are going to take a little while to cover that, and we are going to finish with range view. So this is kind of an overview of a big chunk of what makes this lecture. So positional access is what you expect from any sequence. Okay, so when you are using array, you will use the square bracket notation to index, an element in an array. Well, here we can do that with get, set. Remember the example that we covered last session? So if you start using get and set in a list, be really careful. Don't start mixing that kind of index-based access with, for example, call to remove, or call even to add all. That would also perturb things, okay? So be really careful when you try to mix positional access with, the kind of iterators we are going to cover in a few minutes. Search features are new also in list. So mostly we are going to cover index of and last index of, which allow you to identify the position of sublist inside of list. And then we'll talk about iteration. So we'll talk about iterator, which you've seen already in action, okay? Well, there is another subclass of iterator that's called list iterator, which is just doing the same job, but adding a few features based on the fact that we know the order of the element. So at the collection level, when you ask for an iterator, you don't know really what you're going to get, okay? You just know that you can, at the very least, go through every element of the collection. That would be the required base feature for an iterator, right? But you don't know if the order is going to be the same every time you use the iterator. With list, we know it is. That allows us to go backward and do things like that. And then we'll talk about range views. So I did tell you at the beginning of this module to skip the chapter in the textbook about views. This is the only view that we are going to discuss, okay? But it's really actually it's simple to use, and it's a good illustration of the entire breed of techniques there. So let's talk a little more about positional access and search operation. So these are the methods that we are going to go over. Get and add, no problem. Okay, get, you pass an index. It's going to return to you that element. Add, you just specify the element you want to add, like with the add method from the collection class. But in addition to, you can specify also an index. So you can say exactly where in the list you want to add an element. Set and remove, same thing, nothing really like transcendental there. The only thing to pay attention to is that they return the old value. So if you set something, you are overwriting an element of the list. You are replacing an object reference by another. Okay, so the old reference is going to be returned to you. Same with remove. You try to remove the current, the next employee in your list, based on the iterator. Well, you are going to get this reference so that you can do something with it, save it, do whatever. Okay, so it's kind of like a pop operation actually from a queue. Index of and last index of, well, they respectively return the first or last. Actually, they return respectively the index of the first or last specified element in the list. Okay, the sentence there is a little wonky. Sorry about that. Add all, nothing really transcendental there either. You just take all the elements of the specified collection, the one you specify as parameter, you add it to your target object. The only thing here is that, and this is the next remark, I guess. Yeah, there we go. The elements are going to be kept in order. Okay, question?
Yeah, in the index of functions, if say I have a list and I've made sure that while adding something to the list, I'm making sure that it's a unique element. So I just check whether the list contains a specific element or not. So in that case, if I use index of and last index of, are they going to give me the same result?
Yeah. So the question, trying to summarize it, is pretty much if I have multiple, if I have a single occurrence of an element in a list and I call index of and last index of, are they going to tell me the same thing? Yeah. That's the point. So I guess if you wanted, you could test for the unicity of an element in a list, right, by calling those two methods, but there are better ways. And that's it pretty much. So we have just like completely analog things. They should be trivial. Okay, just let me know if there are any questions there. But it's just that every time we have a feature, we have that feature plus a positional information that we can add as parameter. Okay. Regarding implementation, so the list is an interface, okay, in the Java collection framework. So we have two implementations. We already mentioned that last time, the array list and the linked list. Like the name implies, the array list means that your list is actually implemented as an array. Obviously, the array is going to be resized automatically by the class array list, so you never have to worry about do I need to test if my array is full before to add an element at the end or something like that. Okay, so this is taken into consideration for you. And then the linked list is exactly what it sounds like. Okay, that means that you drop the array implementation, so you don't have direct access to the element. You have to actually go through your list to be able to find anything. So the differences, they translate essentially in complexity. So who is not familiar with the big O notation? Never seen it before? Never? Okay. So the big O notation, like the Redux in like 30 seconds, is just a way to do algorithm analysis. Okay. For example, if you give me a list of n elements, and the task you charge me with, so the algorithm you ask me to write, is display every element in the list. Okay, so I could tell you gave me a list of 50 names, and it took me 0.35 seconds to display it. And that's awful. That's awful because you don't know what JVM I'm using, what version, what operating system, what hardware. So timing execution of algorithm is actually a very bad way to measure their performance. Okay, it combines all sorts of stuff. So instead, what you would look at the code itself. You would look at the algorithm you're using. Well, to display all the elements of a list, right? I iterate first element, second, third, fourth, etc., up to the end of the list. Okay, so this is where this notation comes from. What is the worst case, scenario? What is the average case scenario? How long is it going to take me? Well, it depends on what? It depends on the length of the list. So if I call the length of the list n, okay, I mark my input data size as n, okay, then I can say that this algorithm that just go over every element is of complexity big O of n. Okay, that means that it's going to always be proportional to the number of elements in the list. You give me a list of 50 millions, okay, 500 millions, where the difference between 50 million and 500 million is going to be magnitude 10, okay? An order of magnitude is going to be times 10, all right? So, and that's regardless of how fast my computer is. So if it takes me 10 seconds today, and in 2 years it takes me 1 second, it's going to be still a factor 10 between the two. Okay, that's the idea, very simplified, of complexity. Okay, so what we're looking at here is a list is not just a list. Okay, the list is a nice abstraction. It's a nice interface to work with. You should always program to interfaces, no problem there. But sometimes you need to know actually what kind of performance you're going to get with the implementation. So this is pretty much your summary slide. If you have like some question, some multiple choice question or whatever as exam that asks you to pick between an array list or a linked list implementation, this is the kind of stuff you want to look at. Okay, so let's take a quick look here at this table. So first column, we have different operation. So get with an index, all right, add an element, we don't specify index, then we specify the index, that's the third method, remove an element at a specified index, use iterator.remove, so that's what we used already last time, right? We were iterating through a list, and then we try to remove the current element that we were looking at. And then use add the method from the list iterator, which allows you really to insert things, okay? So when you say I want to add an element of class E, you mean at my current position given to me by the iterator, I want to insert that element, okay? So the complexity are what we're like interested in to make a fair comparison. So if you are looking at the get operation, it's actually pretty clear where you should go if get operations, based on an index are actually your bread and butter in your program, okay? It makes sense. With a linked list, the complexity is going to be linear, so it's going to be big O of n. More specifically, if you want to be like really picky, in this implementation, we are big O of n divided by 4, okay? So why n divided by 4? This is average. This is average performance, and it's influenced by the fact that the Java implementers were smart enough to decide, okay, I have a list that has 50 elements. If you want to access the 49th element at the end, I'm going to start, iterating through the list to find it from the end. If you try to access the 10th element, it's closer to the beginning, then I still have to go through every element of the list until I find it, but I have a choice, start by the end, start by the start, right? So I'm going to be smart and I'm going to start by the shortest one. So that's why you get that weird complexity O and 4 and divided by 4. But basically what's important is it's linear. And the big difference is that this one is constant, which means that whatever time it takes to look up a reference in memory, go through that indirection, that's the time it's going to take to access any element regarding of its position in the list. So that's why that's a criterion you want to use actually to decide whether you want to use array list or linked list. All of this how is it? Is it trivial? Is it back in the days where you took data structure, you already covered that, or yeah? Okay, so we should be mostly good. But don't hesitate to come to office hour if you need a little refresher there, okay? Yes?
Big O of 1 is good or big O of n by 4 is good then?
Say that again?
Which one is like better? Big O of 1 or big O of n by 4? Like which we should go for?
Okay, so when I ask you guys if you're okay with that, if you have this kind of question, you're not okay with that, okay? No, but it's a good question. But what I mean is that don't just let me go on, and move forward, etc. And then you're like, what the hell is he talking about? So, okay, big O of 1 is better, okay? Because it's constant time. So that means that it's just a factor of whatever hardware you're using, your library, your implementation. It's not dependent on the size of your data. So if you ask me, I want to get element number, let's say 1000, and your list has 2 million elements, and then your other list has 2 billion elements, well, big O of 1 tells me that the time to access that element at that index that you specified is not going to change. So if you are going to use a lot of data, yes, constant time is the holy grail, right? But watch out, because here we are not saying that array lists are big O of 1 and then linked lists are big O of n or something like that. Now, we are only talking about one operation here, right? We are only on the first row of the table. So that means that if you find that in your application you are constantly doing get with different index values, and that's actually the most prevalent operation in your code, then yes, that means that you gain a lot by going to an array list. If you never use the get method with an index in your code ever, well, then let's wait, and figure out which one of those methods you're using the most in your code, and that will give us a good hint about, whether array list is better or linked list is better. Okay, so we cannot just say one is better than the other based on one method. It depends what you're using. Okay. All right. Yeah.
Like in linked list, you told that if I have 50 elements in my linked list, so depending upon the number, it will start from the front or from the back.
Yes. That is the implementation of get of index for a linked list. Yeah.
That is in a sorted case. If my linked list is sorted, then only I can start the number from the beginning or from the end. If my linked list is not like in a sorted order, how can I decide that I have to start from the beginning or from the end?
Okay, so the question is in the linked list implementation of get of index, we are smart enough to start from the end or the front, but that presupposes a sorted list. No, it does not. when you do get of index, you do not need to have your list sorted. Your list can be in whatever order. It doesn't matter. What you are saying is, I want element index, let's say 13. So your elements themselves are not sorted. Like, for example, if you have employee, they're not sorted by salary, they're not sorted by name, none of that stuff. But they are in a sequence. So you could say, I guess, that they are sorted by index. I don't think many people would say that about a list, okay? But it kind of makes sense, okay? There's an internal consistency there. So when you say I want access to element number 13, yes, your list has to be in a sequence order, but that's the definition of a list. And that's completely independent from the notion of actual sorting of the element based on a criterion that depends on their data, okay? So you could have a list of objects and you still have a sequence, even though you have no clue about what's actually inside your objects. Okay? All right? So everybody okay for a question about array list or linked list at the exam, right? Okay. So next one, let's talk about add. So add is interesting. It's just one of those methods that actually show implementation detail, okay? By the way, never be fooled by the expression implementation details. Details are the only thing that matter, okay? Everybody understands heart surgery. You cut it open, you spread it apart, you take the tube, you connect it to everybody understands the principles of heart surgery, okay? To become a heart surgeon, you have to deal with the little details, the implementation details, right? Same thing for you guys. You're going to be IT professional. Never go well, this is an implementation detail, it's not for me, right? Oh no, this is exactly where you come in, all right? Everybody else can understand the big picture. So, in add element, the linked list is big O of 1. That means constant time, right? So constant times mean I'm going to always add at the front, for example, or even if I add at the end, I can build my data structure so that it's easy for me to find the end of my linked list, okay? So that's it. To me, adding an element without specifying the index just means always at the front, always at the end. I have a reference that point there. It's constant time. I don't care how big the list is. Array list, well, you would assume that because you are constant time, for getting any element anywhere, if you want to add any element anywhere, a natural reflex would say, well, yes, I can just go at index 13 and I'm going to add my element there. Well, yes and no. If everything goes well, on average, you're going to maybe get O1 on average or something like that. Depending on what you're not going to get it on average. It's the best case. The best case is going to be O1. But the worst case is going to be O of n. So you go back to linear time. And it's kind of counterintuitive when you have direct access. But the idea is that since we implement our list internally with an array, okay, what we do is when you create an array list, I'm going to say, okay, I'm going to have an array, or let's say, I don't remember what the exact number is, but an arbitrary number, for example, 20 element. So now I have an array of 20 element that's empty. That's my empty array list, okay? And then you add one element. I'm okay, I have room for it. You add a second, a third, a fourth, up to 20. You keep adding element at the front or at the end, let's say. Well, that's easy for me. I just go to the next index, put your element there, go to the next index, and so on and so forth. And then what happened? You add a 21st element. Well, the array list allocates a bigger array, copies all the pointers that you had before, and then add one element. So it doesn't allocate an array with one more slot, because it anticipates that you're going to keep adding, and that would be really poor performance. So it's going to allocate, for example, an array of size 40 total, so that it can show your 20 initial elements, and then keep, fulfilling your request. Well, what's going on here is exactly that. When you add and you exceed the capacity, you need to either extend the size, of the initial array by pushing the limit at the end where it says this is where my memory stops for that array. If you can do that, you're lucky, everything is good. But if there is something else in memory right after your array, okay, your array of 20 elements, then you're messed up. you're messed up. You need to allocate another array of 40 elements elsewhere, and you need to copy the references. How many references? Depends on the size of your data. Question?
Yeah, so question. So these mechanics could be realized, like implemented with C function real. Yes.
Yes.
Alloc and real, and
Yeah.
you do not need to copy all elements.
Yeah.
So it's kind of strange decision to copy all elements if you can just reallocate the same memory like we have before and reallocate some memory.
Well, it's not that strange. So the question is, if we look at down there, at the implementation level, we drop down to C language, for example. Well, so the C language has two ways to allocate memory. Alloc, more than two, but yeah, it has a way to allocate with malloc, for example, and then to realloc the memory. And realloc is a primitive that allows you to do exactly what I was describing, which is I don't want you to find another spot in memory that's bigger. I want you to take the current array that you have, but look at the end of the array, at the memory after the array, and if there's nothing there, just extend the boundary, okay? So that's the most efficient way to reallocate, to resize an array. Agree completely on that, okay? The problem is, how do you know that there's going to be nothing after you in memory? And when I say you, I mean that array, okay? If the heap is clear, there's a hole in memory that's big enough to accommodate you, yeah, by all means extend. And actually, the Java implementation, I would bet money actually that this is exactly what it's going to do. But there is no guarantee that, for example, after your array of 20 elements, you don't have another employee object sitting there in the heap. In which case, this is a worse scenario. And that's what the ON is. It's the complexity in the worst case. So you have to actually reallocate your array. Now you could say, well, let's do a little bit of planning ahead. So when you ask me, I want an array list, as I told you, for example, the JVM is going to allocate an array of 20 elements, okay? Well, you could say, what about you give me just 1 kilobyte of padding after? Just padding, empty memory that's not going to be used, so that I know that eventually I'm going to resize, right? So I'm going to resize, I'm going to use that memory, everybody is happy, and I'm really efficient. But that boils down to saying, instead of, give me an array of 20 elements, well, then we just have to say 50 instead of 20, okay? So tuning that kind of stuff, actually that's not a field I've ever been interested in, okay? But tuning that kind of stuff could have consequences on applications that are really performance sensitive, okay? You could actually go down there in the JVM and say, I want to change that parameter. I want to change the default size of an array. You could do all sorts of funny things, You could even use machine learning to try to adapt the behavior of your JVM to the runtime profiling of your programs, right? So all of those things are interesting. I don't know what the state of the art is for that kind of stuff. I'm just guessing that if you are really developing an application that's that performance sensitive, then you're probably better off, dropping to the C level. Okay, C level or C++, or even Objective-C, okay? iOS developers are managing their memory themselves, so they're doing alloc and dealloc pretty much by hand, okay? So all of those classes of language allow you to have a much tighter control, I would say, on allocation and deallocation of memory. And therefore you can optimize because you know what your application needs, okay? What we have here is we have the same difference between what is it called, automatic gear shift, and manual gear shift. Some people want a manual gear shift because they want to optimize the transition between gears. That's fine, but most people are just happy if they can avoid collisions on the road, right? I'm in that camp, so I'm happy as long as I can keep my eyes on the road, avoid bumping into people, and I'm perfectly happy with the default suboptimal system that takes care of all of the gear shifting for me. So if you are in that case, this is safer. Okay. The one thing that's annoying is if you are using a low-level language and you really do not use it for the good reasons. So you find yourself re-implementing worst-case scenario, you re-implement your own version of array list. Okay. Good-case scenario, you're using a low-level language like C++, but fortunately it has actually a nice template library, so you have an equivalent of array list that's been implemented for you. Okay. In Java, you don't have that choice. So if you go with Java, you want actually clean code that works. You want to try to avoid bugs. You don't necessarily want, to speed up your application in a crazy manner. All right. What else? So add an element at a specific index. So this one kind of looks like the first one, right? We are trying to do direct indexing. All right. So we can start at the front or at the back. If the index is always 0, of course, or even actually if the index is the size of the list, there should be an optimization kicking in that allows you to do constant time for a linked list. Okay? For an array list, the average is big O of n divided by 2. So why n divided by 2? Because of shifting. Okay? So you have an array. Let's say you have an array with 5 elements, so all of them are occupied. Now you want to insert something in the middle. So if I want to insert at index 0, 1, 2, which is roughly the middle, then what do I need to do? I need to push those 3 elements that were at the end. There's no way to insert in the middle of an array. Okay? All you do is you copy each element and shift them to the right, and then put your element in the spot that you just cleared. Yes, question?
Suppose my memory does not have that space at the end of the array, then what will it do?
Okay, so question is, whatever happen if I don't have memory at the end of my array? So in my example right now, I was assuming that the array list was not at capacity, okay? Meaning that I had 5 elements in my array, okay? But that's a difference that is really worth understanding. You can have 5 elements in an array list, but internally, the array that is used to store your element can be of size 20. That's the whole point of array list, right? Array list is going to allocate a bigger array. Okay, I told you when you have an empty array list, Java is going to do something like allocate an array of size 20 to store all your elements. But you have 0 right now. So the size of your array list is 0 from the programmer perspective. From the implementation of the array list class perspective, your size is 0 element, but your capacity is 20, right? So when I said in my example, like 30 seconds ago, when I said, let's say we have 5 elements in an array, I'm talking about size. Okay? So I have 5 elements in the array, but I didn't say anything about the capacity of my array list. So your question comes from the assumption that capacity and size were the same. When capacity and size are the same, you're right. Then we fall into the worst case scenario where we have to shift. Okay? If capacity and size are not the same, if my size is lesser than my capacity, then I don't have to resize the array underneath. But if I insert something at index 2, I still have to shift, the over 3 elements that are at the end. Okay? So I shift them. I don't have to resize the array. I just shift them. On average, what index are you going to use? Assuming a regular distribution, you're going to use an index that's towards the middle, half of the time, whatever. That's what gives you the O n divided by 2. Okay? But we're not in an algorithm analysis class, so all we care about it's roughly linear. That's the key. Whether it's n divided by 2, n divided by 4, n divided by pi, don't care. Okay? It's roughly linear, so you want to spot in this table the clear distinction of performance. In that example with list, it's easy. It's between constant time and linear time. So wherever you see constant time, you want to go for that. Okay, that was a question sooner. Which one is better? O1, big O1, big O(n)? Yes, always big O1. Okay, so depending on what your program needs, you are going to try to focus on those green cells here in the table. What about remove? So this one, again, like get and like add for the linked list, O n divided by 4 on average. Okay, so start at the front, start at the end, etc. The difference is less critical here between linked list and array list. You can see that the implementation in array list is going to be big O n divided by 2 on average, so a factor of 2 between the two. Okay, so that matters, but in the grand scheme of things, it really doesn't matter that much. Okay, when you look at algorithm analysis, one thing to understand is that anything that is a constant factor, okay, like a big O1 doesn't mean that it takes 1 second. So anything that is a constant factor means it's not going to change with your data. Then when you say big O(n), well, it might change by, it can change linearly, So if I go from 10 element to 20 element, yeah, double the time, okay? But if the complexity is big O of 2n, right, there is still this linear difference between the two sizes. So that's why we simplify generally. We look at linear time, quadratic time, cubic time, exponential time, factorial time. These are the big categories that matter. Question?
Yeah.
Yeah.
Suppose my capacity is full and I have to copy that to another memory location. That is done automatic, correct?
Yes. The reallocation of an array inside of an array list is automated.
Okay.
You don't have to worry about that.
The old array list that is left at the memory spot, is it removed by the array list or is it removed by the garbage collector?
Okay, so the question is, let's say that I exceed capacity of my array list, so I have to reallocate a new storage for the array list. What happened to the old storage? Is the array list implementation pretty much deallocating it, or is it taken care of by the garbage collector? This is Java, it's taken care of by the garbage collector. Okay? Now, I think I remember vaguely that there is a way to force actually the garbage collector to kick into action. Never used that personally, so this might be something that's available. I don't know. There's also a body of work on tuning garbage collection. Okay, so some people deploy JVMs and actually tune the parameter of the garbage collection algorithm. But again, if you care about garbage collection, the worst that can happen with garbage collection is you have a GPS software that's running in your car. So anything that's kind of like time sensitive, and the GPS software tells you, you need to turn right when you come in front of the fork in the road. Okay. Well, let's say that the GPS is at the point where it's about to tell you turn right, and then garbage collection kicks in. And garbage collection is going to take, realistically, it's not going to be that long. But just for the case, let's say that it takes 2 seconds. So you pass your intersection, and then the GPS tells you, hey, you need to turn right. Okay, so anytime you have real-time application, this is a bad example, but anytime you have real-time system, real-time application, you don't want to use garbage collection. Question?
In Java, garbage collection is performed in the same stream or in the same thread, yes? Not like in the separate thread.
Okay, so the question is garbage collection done in the same thread than your application or not? Not sure. I have to check. That's a good question.
Probably there is 2 modes. I know for .NET there is 2 modes. Like you can execute the garbage collection separate.
Well, if it's in a separate thread, that kind of takes care of that kind of problem. Okay, but there are still, I don't see a lot of people reporting that they use Java or any even garbage collection that's implemented in another language when they have to deal with real-time system. Real-time system actually, they are more complicated than the example I took, because that was really like a simplified example from a person that doesn't do real-time system. But if you're considering real-time system, you want to have hard-coded constraints about the time of execution for all of your thread, your processes. So it's kind of like a different style of programming together. Okay. Generally, people that have to deal with those kind of system, they kind of specialize in it and deal with a lot more constraint than what I can illustrate for you.
But Java and the .NET languages, they are not good for real-time.
No.
Because it's
Well,
compilation at runtime, yes, so this stuff and garbage collection they will prevent to determine the limits of the time, yes?
yeah. So the remark was, Java and .NET are not good for real time. No, they are not good for real time, for real time application. Okay, but to go one step further, when you are really developing, an embedded system like with sensors, etc., like something that has to do with robotics, and real time becomes really essential. I didn't forget your question, by the way. I'm just finishing. But and real time become a concern, then even more than your JVM, okay, you need to worry about your operating system. For example, like the basic version of Windows, I don't even think there is a Windows version that's real-time. There are versions of Unix systems, Unix kernels, that are actually real-time, okay? But these are specific operating systems that provide those features and provide guarantees about what's happening. Because the garbage collection is not the only thing that can happen independently of your flow of execution, okay? We love to abstract things. We love to say, my program has access to the entire memory available on the system. It's not true. You share it with other processes, okay? So the further you go from the hardware, the less likely you are to be a good fit for real-time application that actually care about those details.
Yeah, I wanted to say that it's better to probably, if you work with sensors, to work on such devices like Arduino, when you have like just one without operational system, like Raspberry Pi has operational system. So it's like another layer, and they will like provide delays, and that's why you need to work with microcontroller at the lowest level in this situation.
Yeah, so the remark was, we can go one step further and say get rid of the OS. So the example that he was using was, for example, if you're looking at doing some domotic projects or stuff like that, the Raspberry Pi runs actually a full Linux distribution on top of the hardware, and that distribution is not specialized, the kernel is not specialized for real-time system RTS operation, okay? But if you are using something like an Arduino, then you can directly upload to the hardware your code, and your code is going to run with full privilege on the platform. So it's a different type of programming. I would say this is probably the difference. I mean, if we are talking about application, to real sensor, physical stuff like that, domotic, etc., that's probably where we draw the line between computer engineering and computer science even. Okay, computer science and IT, we are more on the software side. Computer engineering, then they tend to deal with lower level programming. So the prospect of having to bypass an OS and program directly on the hardware, that's generally not something that sends a good vibe to any Java developer or software engineer or computer scientist and stuff like that. Yes, you had a question?
So when the JVM reallocates the array to a new location, if there is already a reference of that previously declared array, so what happens then? Does it throw an error, or JVM automatically reallocates the reference to the new memory location?
So when you, I'm going to try to summarize your question as I address it, okay? So when you resize your array with the array list implementation, what's going to happen is that, yes, you have a reference to a current storage location. Let's say it was big enough for 20 elements. Now you're looking for a new one, big enough for 40. And then you copy your elements. Once you are done with that old reference, you can simply set that reference to null. Okay, you set your pointer to null, which means you lose the address to that storage that was used inside the array list implementation. If you do not have, the address of an object in memory anywhere in your code, technically you can never use it again. You lost the address. That's where the garbage collector is going to know that it can dispose of that.
So if it's already referring another object, like if I create one more object which is referring to the array list, which was reallocated later, so it will not go to garbage collection because the one object is already referring to the memory location of the previous.
Yes, okay, but keep in mind that we were talking about two references, okay, and I didn't separate them enough, so I'm going to be careful to do that to clarify any potential problem and misunderstanding here. Let's say that you have a reference to an array list object, okay? That reference is not going to change. Even when the array list, internally resizes its storage, okay, that one reference to the array list object is always the same. What's changing, the reference I was talking about, is down there in the implementation of the class array list, you have a link, if you will, to a memory location where you store your element, okay, the reference to your element. That link is going to change. But that's the beauty of abstraction, right? The person that implements the array list class has to worry about that. They have to worry about, I have a reference to this area of memory, now I get a new one, I copy the stuff, then I set that reference to null, this is going to be garbage collected, okay? They have to worry about that. We don't, because we have just one reference to the whole thing, the array list, and that doesn't change, okay? That's a good remark. All right, so we're almost there. So we were talking about remove, at least I think we were talking about remove, yes. Iterator.remove, list iterator.add element. So these are big O of 1, with the linked list implementation. That's the advantage of the linked list. The iterator is kind of like a pointer, a handle on, like pretty much, it stands between two elements of your linked list, okay? So you move to the next, you move to the next. So in front of you, you have the next element. Behind you, you have the previous element, okay? So if you want to insert something, it's linked list spaghetti programming, okay? Call it spaghetti programming because if you visualize this with a diagram, with blocks that are pointing to the next, what you do is you take those arrows, you break them, you put a new element, you connect the arrow on both ends, and that's what adding to a linked list really boils down to, okay? So this is where the linked list implementation shines. It's adding in the middle of things. You'll never have to actually shift your element and do stuff like that. And actually, you'll never have even to reallocate your array, okay? So that's the benefit. You can see the performance is a little less good for a release, so it's linear versus constant time. So if that's what you do in your code, then the choice is clear here. Okay? And that's pretty much it. So again, the green cells, and actually there's two green cells that I'm missing here. The add element and, I guess the add element would be green for both array list and linked list. Maybe that's why I didn't color it, but whatever. So the constant time complexities are really what you want to pay attention to. So if you have any sort of question on, what do I use in this case, then the description of the problem is going to tell you something about if you are doing a lot of get index, if you are doing a lot of insert in the middle, and stuff like that. That's what you use to answer those kind of questions. So let's take a quick example to wrap up this part on list. So we have a swap method here. So we have a swap method. It's a generic swap method. So public static is also a static method. We take a type parameter E. We have a list of E that is our first argument, first parameter A, and then we specify indexes I and J. And what we want to do is we go into the list A, we take element index I, element index J, and we swap them around. Okay, easy peasy. That's actually the example that we started. I think that's course 3, right? So the code here is just, save it in a temporary variable, overwrite one of them, then overwrite the second with a temporary variable, and so on and so forth, okay? So basic swapping like we've done before, nothing fancy. So we use the positional access API here, the get method, to get that kind of stuff done. Then we are going to use that swap. We're going to use that swap to shuffle a list. So that method shuffle is going to be also a static method. We are going to get a list of unknown, so we can work on any list. That's where the wildcard type instantiation are relevant. Okay, yes, you cannot add to that list a lot. You cannot remove from that list and store it in a variable. You cannot do almost anything with that list. But guess what? The little bit that we can do is enough for our application, because we are really just looking at the abstract concept of a list, and we just want to move element around. So we never really deal with elements themselves. Could be employees, could be anything, we don't care. Okay? So this is when you are going to have those list of unbounded wildcards. And then we take an object of class random just so that we can generate randomly indexes. So what we do is we start iteration at the end of the list. So the index I start as the size of the list. We keep iteration going as long as I is greater than 1, decrement I, and then we say I want to swap in my list the element of index I minus 1, so I minus 1 because we started at the size, okay, and that's also why we have to stop at 1, and then a random position in the list. So we take all the elements from the end of the list and we swap them randomly, with some place in the list. And that's actually, I don't know if it's true for Java 9, I didn't check, but for Java 8 at least, and I don't see why it would change, but that's actually the essence of the shuffling method in Java. Yeah.
So instead of using a list of diamond operator E, why did you go for an wildcard?
Okay, so the question is, if you tell me that list of unknown in the second half of the slide is good, then why do I care about a list of E in the first method on that slide? Well, because the second method in the slide, if you look at it, okay, we are calling swap, right?
No, I'm asking why did you go for a wildcard? You could have just used list of E instead in the shuffle.
Oh, in this one?
Yeah, in the shuffle.
But I don't use E.
Yeah, that is why I'm asking that.
Okay, so all right, let me rewind. So the question, I misunderstood the question, was why don't we use list of E here instead of list of unknown? And my answer is you could, but we don't use E anywhere. It doesn't appear anywhere in the code, right? So it's kind of like saying, can I have a third parameter X that is a double to my method? The answer is yes, you can have a third parameter X that is a double, but since I never use X in the method, it's not necessary, right? So in this case, I could say I want a list of E. E is a type parameter, but I never use E. All you did is now every time I want to call this method, I have to specify the type argument, or I have to have Java type inference system, determine it from the context. And really it doesn't matter. We never use it. You see what I'm saying? Okay, and the first way I was answering a question which was not related to your question, actually, was to say, well, you do not need E either here, even for you call swap, okay? Because what you do in this code, in the shuffle code, is completely independent of your element. Now, what you do in the swap method is dependent somehow of your element. You still use a get, so you get yourself in the shoes of a specific role, which is producer or consumer with respect to that list, okay? So at that level, that would be a problem to use a list of unknown, okay? In the first method at the top of the slide. So this one, we need to specify actually a type parameter. We need to make sure this is a generic type and not a wildcard type, okay?
Yeah.
Question?
Yeah, like it has both getter and setter method, and both of them are used at equal, like both of them are used 2 times. Correct?
What do you mean by both methods are used 2 times?
The getter and setter function are used 2 times in the swap method.
Oh, the angular brackets here?
No, the getter a dot.
Oh, the gets and set. Sorry, I misunderstood you. Yes, so get and set are used twice in the swap method. I'm with you.
Suppose it's not just list of E, it's list of something extends or super another. So how can I decide whether I should go for extend or whether I should go for super?
Well, the way you decide whether you need super or extend here is you go back to that previous lecture. We have this table that actually summarizes all the case, right? But the acronym that helps you remember that is PECS, PECS, okay?
Yeah.
Producer, extend, consumer, super.
Yeah, but
So-
it is using both producer and consumer with this method.
Well, then you don't have a choice. You don't super, you don't extend, you just are a list of E. The remark was, well, I'm doing both get and set, I'm both producer, consumer, so then you have to use list of E. You cannot be more generic, I would say, and conserve type safety. Does that make sense? Yeah. Question?
Actually, can we rewrite this method first, swap, because set, it returns your previous element. So we can write it in one line, like a.set g, like comma, a set e, and you see, yes?
Yeah. So the remark is this is unnecessarily long, the swap method here, because we use a temp variable to save what we get, and we use get and set, but we could really just use set insofar as the set method is also returning the reference to the object that you are overriding. So you're correct. And if you do that, then you are not both consumer, producer.
No, we actually need one get. We need one get because on the internal set, like in the inner set, we will have get.
Mm-hmm.
But we then can remove e parameter. We can use like question mark, like wildcard.
No, if you use set, you're still in one of the 2 roles. So you would have to be careful about that. So the next question was, well, if we just use set, we rely on the set doing the get operation internally, then can we use a list of unknown? And no, I would bet you can't, because you are still actually either producer or consumer. And actually, I said something about, well, if you use only set, then you are only in one of the role. But since the set is returning also the reference to the previous element, it still counts as you're both. So you're both producer and consumer, even though it looks like superficially that your code is only doing one of them. So yeah, that's an interesting one actually. That's an interesting source of bug there. I can see. Okay. So, where were we? Yeah, thank you. I just reboot from time to time. That's why I have slides with pop-ups, is that can keep me on track. Okay, that's not for you guys; it's for me. No, I'm kidding. So this is actually the nuts and bolts of how shuffling is implemented in the Java collection framework. Okay, there are two characteristics that are interesting about that very simple algorithm. It's efficient. So assuming that you have actually an unbiased source of randomness. So that's why we pass actually the random object. We delegate the responsibility of creating a random object and seeding it properly, etc. to the caller, okay? So that we don't just call random on an internal seed in our method that would result in the same sequence, a pseudo-random sequence to be generated. And all permutations are going to occur with same likelihood because we just uniformly draw an index at random, okay? So that's the efficient part. And the fair part is actually the interesting one of the two, in my opinion, is that you are going to, actually I messed those up, I think I swapped them. Yes, I swapped them, hold on. Efficient, yeah, efficient is you are going to require exactly list.size -1 swaps, because we have just one iteration from the back to the front, and then we determine randomly where we swap. And the fair bit is actually that all the possible permutations that you could have are going to occur with same probability. So that makes more sense when it's the other way around. So I'll fix those arrows in, I'll upload a new version of the slide where actually I point to the right stuff. Sorry about that. So let's use that shuffler now that we just wrote. So we have a public class shuffle. We are going to take some words from the command line. So we are going to run this program and type a sentence, on the command line. The program is going to take everything that was passed as arguments, so the words of our sentence. It's going to create a new array list. It's going to add to that array list all the elements, and then it's going to use collection.shuffle. So this is one of the algorithms that we're going to mention at the end of this lecture. So it's pretty much an algorithm that's meant to work on any list implementation. Okay, so it's a static, like most of those algorithms provided by the Java collection framework. It's a static method of the collection class. So collection.shuffle, we pass our list, we pass a new source of randomness, okay, and then we display the list after it has been shuffled. Rest of the public class shuffle, what do we have here? Our main nodes. This is the same thing. We are just going to simplify it now. So we are going to take that little bit that's kind of annoying because we create a new array list and then we pretty much add incrementally the element, and as we do so, we are iterating. So we are going to try to simplify this a little. You know already how to do that, constructor, okay? So it's kind of a conversion here. We convert, it's not kind of, it's a conversion from an array of strings to a list of string, okay? So we've done that when we just started dealing with collection. So that's the first simplification. The second simplification is that you can also call collection.shuffle and just pass list, and it will take care of generating a random object for you, okay? Just the one thing that you have to be careful in this piece of code is a little pop-up. Remember that when you do the as list conversion, you get something that is not quite the same thing as an array list, okay? It's kind of a wrapper around an array list. The main difference being that you cannot add elements, you cannot remove elements, okay? You had a question?
Yeah, so if I wanted to create a generic array of type E, so could I create a generic list first and then pass it to the array?
Okay, let me see if I understand your question. If you wanted to create a generic array of type E, where?
I have a question in one of the exercises.
Okay.
So there we have to create a generic array, and we probably have to add elements to the array, and if in case of resizing, we have to resize the array. It's a generic array.
Okay.
So if I want to create that, how exactly can I instantiate it?
So you are creating like a low-level, a regular Java array, right, of type E.
Yeah, of type E.
Okay. All right, so that's okay. That's not exactly what we're talking about here. So let me open a side remark on this. So okay, what is the concept? The context? You are actually inside a method. You take a type parameter e.
I have a basic class.
Yeah.
Which has a class variable which is of type e. It's
Yep.
an array. It's an array of type e.
Okay.
I probably have to add elements to that array of type e, and I might have to resize it in case the array is full.
Okay. So check the restriction at the end of the last lecture, because I think that's one of the restrictions. You are not going to be able to instantiate your array directly using E, if I remember correctly. But you can do it with metaprogramming. But
With metaprogramming, so I was wondering, can I create a list of e,
Mhm.
then assign it, convert the list as an arrays dot as list, and pass that.
Well, isn't that going actually the other way? Because if you create your list of E, then what do you want to do? You want to generate your regular Java array from your list?
Use the list dot as array and convert the list into
Okay.
the generic array. But in that case, will I be able to resize it, because we are not able to resize an array that is passed as a list? So can I resize a list that is passed as an array?
Okay, so the question is, so we have a type parameter E, a type argument E. We are trying to create an array of element of type E. This array, we're not going to be able to create it easily, so we have to go through metaprogramming. You want to avoid metaprogramming by actually creating a list of E, and you create a new array list of E to put inside of it. You put your element in there, then you extract your array from your list by using the asList method. What is the data type that's returned by the asList method? That's your answer.
It's e, so it's going to say that I can't.
No, it's not E, right? AsList. Sorry, asArray. Sorry, I used the wrong name. You have your list, you try to do conversion asArray. What is the data type returned by asArray?
An array of e, basically.
Okay.
It's going to say I'm not able to reference to my get.
Well, then there's no problem of resizing, right, if it's an array of E.
Yeah.
I think both you and I went back and forth between the list and the array, and I certainly got confused in the trip. But if you are returning a regular Java array, then you don't have any question about resizing it, because the regular Java array do not resize, right? So the array list object can resize internally. But if you have a integer, square bracket, equal x equal new integer of 5, that's it. That's your size. Okay? Okay, I think we got it, but
in case of resizing, I was hoping that I could convert the array again into an array list, automatically add
Well,
a value element to it, let JVM take care of.
I think you got sidetracked by the limitation that is going this way, which is, when you extract from an array, you extract a list, you get a weird list, okay? But if you take a list and you extract the element into an array, you do not get a weird array, okay? You get a traditional Java array. Because in that case, what makes it weird here is that it's kind of a subset of the feature you would expect from an array list. So you cannot add remove, which means you cannot resize. Okay? So that's the main bug here. That's the main problem. But if I create a new array, right? I put the element of your list inside that array, and I give you a reference to that array object. It's a regular Java array object. Okay. So that's good. You guys are starting to come up with some tortured scenario. That's really good, actually. That's what I mean, by the way, about playing with examples. Okay? You need to get to a point where you break things. You need to get to a point where you have to test them hands-on. And that's actually how you're going to really validate your theories. Okay? It's kind of like Science 101. You have a theory. You design an experiment to validate it or not. In our case, things are easy because when we have a theory about, okay, can I modify this list here or not? Can I resize it? Can I add or remove? I don't remember what the JVM does. It's easy. You open a side window, you write a 10-line program, a 5-line program that just validate that hypothesis. And you know either way. So I don't ask you necessarily to remember and memorize by rote learning all of that stuff, But if you don't remember during an exam, you have to be able to open a quick window, do a 5-line program, a class with a main, and test it out. And then you'll have your answer. That's why I do an open book exam. That's why I allow you to use the IDE. Okay? So that's very good. All right. So we are going to probably finish with this and leave the last part for Wednesday. So iterating on lists with iterators, we are going to look at quickly at 2 different ways, so iterator and list iterator. So I already mentioned that the latter is a subclass of the former, okay? The list iterator, the main thing that it does for you is it allows you to go both ways, forward and backward into your list, okay? And that's because the list guarantees a sequence order. So a collection in general, all you can say is I'm going to iterate over every element. No concept of order, so no concept of going forward, backward. With a list, well, yes, now we can say we're going to iterate in the order that the elements have been inserted in the list, but because I have this order, now I can go backward, go forward, move like that, okay? So we have the same way we have as next, next, well, remove is the same for both, but as next and next allow you to move forward in a common traditional iterator for a collection, okay? So these are still available. They do exactly the same thing. And then we have 2 new methods, as previous, and previous, that are exactly the analog of the other ones, okay? I was going to say of the previous one. It's a little confusing, but so the same thing you can test if you had an element before you. So when you start iteration at the beginning of the list, this is where you are not going to have a previous element, okay, to start off with. And then the same way you do next to consume the next element, actually have a reference on it ready in your iterator and go to the next element, you can do previous, okay? So always imagine that your iterator is a handle pointing between 2 elements of a linked list, okay? That's the best way to run through those problems and debug them, okay? And if you are curious about this, you want actually see some edge cases and stuff like that, check the Java tutorial. There is a section of the Java tutorial, the Oracle Java tutorial, that has skipped actually in the slide, but that goes at very, very long length, on explaining, how that handle works and sit between 2 elements. Question?
So I'm hoping the has next element and has previous element, the functions are going to return Boolean values, saying that.
Mm-hmm.
the next
Yep.
element. So I like to say that in case I have a list of, say, my capacity is I have an array list. I have a list which is referencing to an array list. So by default, I have 20 capacity of 20, but my current size is 5 of the array list. So if I'm on the 5th element and I'm creating an has next, I'm calling a has next. Is it going to give me a null pointer exception as in that case?
Okay, so the first remark you made is, okay, so I'm assuming as previous, as next, return a Boolean. Yes. And then the question was, well, let's say that I have a list of size 5, an array list of size 5, and the capacity is 20. So I already iterated through the list. I'm standing after my last element. I call as next. Do I get what? A null pointer? Do I get an exception? No, you just get false. Okay? The as previous, as next is working from the perspective of the programmer using the array list. So what do we care about? Do we care about the internal capacity? No. I just care about knowing whether there is actually a next element stored in that list or not. So if you tell me I already went through the 5 of them, then as next returns false. Okay, regardless of how much capacity I have. So here's an example of iteration. I think we have 2 more examples, 2 slides, and then we are done. So right in time. Iterating backwards, so that's one of the things you can do with a list iterator also that I didn't mention yet. When you actually create your list iterator, you can say, I want the list iterator to start at this index. So in this example, we put our handle, okay, that's internally managed by the list iterator, we put it past the last element. So we use index list.size, right? So we are completely at the end of the list. And we do exactly the same thing that we've done before with, as next and next. It's simply that we started at the end of the list. So we use as previous as condition for our for loop. And then every time we want to get the next element, we call it.previous. Question?
If you don't pass the list.size parameter, does it start from index 0?
Yeah, it starts from the start. Yeah. So the question was, well, what if I don't pass list.size? You have a default behavior which is starting at the beginning of the list. Okay? And then the last example here, this one is actually interesting, but not so much for list, just for that little programming trick, I would say. So we have a replace method. Takes a list, takes a value which we want to replace in the list. So we assume this value is in the list. I mean, we don't assume, we're going to check, okay? And then the new value that we want to insert in the list to replace a val. So we have a list iterator. We start at the beginning of the list. We go forward, so we test as next. And then this is an interesting bit, that if statement inside the for loop, okay? So we first distinguish between the case where val is null or not. So you can have null element in a collection. Remember that, okay? That doesn't mean the collection is empty. So if val is not null, then we have pretty much two nested if statement here. So we have a ternary conditional operator that says if val is null, then I'm going to test whether the next element is null. If the next element is null, then I replace it. Okay, set is going to replace whatever next would return to you or has returned to you. Okay, and then if val is not null, then I just test whether val is equal to my element obtained by it.next, and if so, I replace it. So why do we bother on this? Well, we bother doing this because if I wrote simply if val.equals it.next, okay, well, if val was null, I get a null pointer exception. All right. So that's hang in there. Next module, we're going to do this kind of stuff in a way that doesn't make you nauseous. But this is actually the kind of stuff you have to worry about when you have like potential null pointers, and it's a separate case, and you have to handle it separately. So that kind of make your if statement sometimes complicated. So I lied, we had one more. The last thing we are going to cover is actually the same example, but instead of replacing one element by one value, now I get a list of new values. So I want to replace one element in the list by a series of different values. It works exactly the same way. Okay. The only thing is that instead of doing set, I do remove to get rid of that element, and then I use a loop to add all of the other elements after that. Okay. All right. We are going to stop here because I have 1 minute to spare. So we're going to stop here, and if you have any questions, drop by office hour. Don't hesitate, and I will post an announcement about the exam as soon as I'm back in the office, okay?